Welcome to Module 6, Data Storage and Operations. This is Chapter 6 of the DMBOK, worth about 6% of the exam. This chapter is the most infrastructure-flavored of the knowledge areas. It's where the database administrators live. We'll cover the famous trio of ACID, base, and CAP, the different database architectures, and the operational realities of backup, recovery, and availability. Let's dive in. Here's our plan for this module. You'll define data storage and operations, including its two sub-activities and three goals. You'll identify the different DBA types and database architectures. You'll compare ACID, base, and the CAP theorem, which together are the most testable part of this chapter. You'll describe how databases are organized, hierarchical, relational, and NoSQL. You'll explain replication, recovery, and the key metrics RPO and RTO, as well as the availability factors. And you'll recognize the database environments, the data migration phases, and the governance metrics. Let's start with the basics. The DMBOK defines data storage and operations as the design, implementation, and support of stored data to maximize its value throughout its lifecycle. It splits into two sub-activities. Database support covers the data lifecycle work, implementation, backup, purging, performance. Database technology support covers the technical side, architecture, and installing and administering the technology itself. There are three goals: manage the availability of data across the lifecycle, ensure the integrity of data assets, and manage the performance of data transactions. And the primary business driver is business continuity, because if a system becomes unavailable, business operations can grind to a halt. So if you're asked the driver for this knowledge area, the answer is business continuity. Database administrators follow 5 guiding principles. 1. Identify and act on automation opportunities to shorten development cycles. 2. Build with reuse in mind, using abstracted, reusable data objects to avoid tight coupling. 3. Understand and appropriately apply best practices, being flexible rather than dogmatic about them. 4. Connect database standards to support requirements, so the service level agreement reflects the methods the DBA recommends. And 5. Set expectations for the DBA role in project work, and importantly, that means onboarding the DBA during the project's definition phase, not at the end. The recurring theme: bring the DBA in early. The database administrator is described by the DMBOK as the most established and most widely adopted data professional role. There are several specializations. The production DBA handles operations, performance, backup and recovery, clustering and failover, archiving. The application DBA owns one or more databases across all environments, from development through production. The procedural DBA focuses on stored procedures, triggers, and user-defined functions. The development DBA handles data design and the sandbox exploration environments. And the network storage administrator, the NSA, manages the hardware and software supporting the storage arrays. Note that the procedural and development DBA functions are often combined into a single position, and the DBA generally serves as Level 2 technical support. There are 3 architecture types to know. Centralized means all the data lives in one system, simple, but it creates a single point of failure. Distributed means multiple databases across multiple systems, typically on commodity hardware, designed to scale out, with software replicating data for high availability, and some distributed databases use MapReduce, which splits a data request into many small fragments co-located on the compute nodes. The third type, federated, is the subtle one. A federated database provisions data without any additional persistence or duplication of the source. It maps multiple autonomous databases into a single federated view. Crucially, there's no actual data integration, data interoperability just manages the view. Federation comes in 2 flavors: loosely coupled, where each component database builds its own federated schema, and tightly coupled, where independent processes build one published, integrated schema. Federation is best for heterogeneous, distributed integration and master data management. Here's a fact the exam likes: A blockchain is a type of federated database used to securely manage transactions, financial transactions, contracts, health information. It has two structures, individual records and blocks, and each block contains information from the previous block, forming the chain. Hash algorithms generate the block information, and once a new block is created, the old block's hash never changes. That's what makes a blockchain immutable. If someone tampers with the data, the hash values no longer match, and the tampering becomes obvious. On the cloud side, there are three ways to deploy databases: a virtual machine image, where you run the database on a VM, database as a service, where the provider installs and maintains it and you pay per usage, and managed database hosting, where the cloud hosts and manages it on your behalf. Remember, blockchain is a federated, immutable database. Now the first of our three big acronyms, ACID. The term was coined by Herder and Reuter in 1983, building on a concept established by Jim Gray, and it's been the indispensable reliability constraint for database transactions ever since. ACID dominates relational storage. The A is atomicity, all of a transaction's operations perform, or none of them do, it's all or nothing. The C is consistency, the transaction must meet all the rules, with no half-completed transactions. The I is isolation, each transaction runs independently of the others. And the D is durability, once a transaction is committed, it cannot be undone, even by a crash. Two to remember most: atomicity is all or nothing, and durability means it survives a system failure. The counterpart to ACID is BASE, which arose from the explosion in data volumes and variability, the need to handle unstructured data, read-optimized workloads, and flexible scaling. BASE is common in big data environments and at large online and social media organizations. The B is basically available, the system guarantees some availability even when nodes fail, though the data you get back may be stale. The S is soft state, the data is in constant flux and isn't guaranteed to be current. In fact, the state can change over time even without new input, as data propagates. And the E is eventual consistency, the data will eventually become consistent across all nodes, just not at every single moment. The trickiest of these is soft state, so remember, the state can drift over time as replicas sync. Let's contrast ACID and BASE, then introduce CAP. ACID uses schema on write, the structure must exist before you write, with strong consistency, rooted in 1970s relational systems. BASE uses a dynamic, schema on read approach, with consistency that may be strong, eventual, or none, and it emerged in the 2000s for unstructured data. Now the CAP theorem, also called Brewer's theorem, from Brewer in the year 2000. It was developed for distributed systems, and it states that such a system cannot comply with all parts of ACID at all times. The practical formulation is pick 2, shown as the triangle on screen. At most two of three properties, consistency, availability, and partition tolerance, can hold in any shared data system at once. The key scenario: if a network partition happens and you choose to stay available, you must sacrifice consistency. CAP equals pick 2. Beyond architecture, there are three ways to organize a database, and they're not mutually exclusive. Hierarchical is the oldest model, used in early mainframe systems. It's a rigid, tree-like structure with mandatory parent-child, one-to-many relationships, think directory trees in XML. Relational is named, interestingly, for relational algebra, which is set theory, not for the relations between tables, which is a common misconception the exam exploits. Relational uses SQL, schema on write, and is row-oriented. And non-relational, or NoSQL, which stands for not only SQL, uses schema on read and aims for improved performance, especially latency and throughput. Two relational variants to know: the multidimensional variant used in data warehousing, queried with MDX, and the temporal variant, where valid time plus transaction time gives you bitemporal support. And a key pairing: OLTP is row-oriented, OLAP is column-oriented. Let's enumerate the non-relational types. Column-oriented stores compress redundant data and are well suited to OLAP and BI workloads. Spatial databases are optimized for geometric and geographic data using a spatial index. Object or multimedia databases use a hierarchical storage management system. Flat file databases store rows and columns in a single file with no relationships between records, and notably, Hadoop uses flat files. Key-value databases include document databases, which use XML or JSON, and graph databases. And triple stores store data as subject-predicate-object triples, that's the RDF format, making them ideal for taxonomies, thesauruses, and linked data. To anchor for the exam, triple store equals RDF subject-predicate-object, and flat file is associated with Hadoop. There are several routine database processes worth knowing. Archiving moves data to lower performance media, and you must align it with your partitioning strategy and regularly test that you can restore it. Change data capture, or CDC, detects that data has changed and is sometimes called log-based replication. It's non-invasive and works either by data versioning or by reading the logs. Purging completely removes data, and here's the key point: purged data cannot be recovered. It reduces cost and liability. Replication keeps the same data on multiple devices. Retention defines how long data is kept and is driven by regulatory compliance. And sharding isolates small chunks of a database so they can be updated independently. The exam contrast to remember: purging is permanent and unrecoverable, while archiving moves data but keeps it retrievable. Let's go deeper on replication. There are two main patterns. Mirroring replicates updates immediately using a two-phase commit. It's more expensive and works well when you have a single secondary. Log shipping sends the secondary the transaction logs at regular intervals. It's cheaper and is used when you have additional secondary servers. Replication can also be active or passive. Active replication recreates the same data at every replica from every other replica, while passive recreates it on a single primary and then pushes that state out to the secondaries. And you can scale replication two ways: horizontally, meaning more replicas, or vertically, meaning replicas that are geographically further apart. The key contrast: mirroring is immediate and two-phase, log shipping is interval-based. The DMBOK names three recovery types. Immediate recovery is handled through design, like automatic failover. Critical recovery means you restore as quickly as possible to minimize downtime. And non-critical recovery can be delayed until the more critical systems are back. Now, two metrics that the exam loves, and that people constantly mix up. Picture them on the timeline on screen. RTO, the recovery time objective, is about time, how fast you must restore service, the maximum acceptable downtime. RPO, the recovery point objective, is about data, how much data loss you can tolerate, the maximum age of transactions you might lose. So if an SLA says restore within 4 hours and lose no more than 1 hour of data, that's an RTO of 4 hours and an RPO of 1 hour. Lock that distinction in: RTO is time to restore, RPO is acceptable data loss. Organizations maintain several database environments, and you should know their roles. Production is the mission-critical, real environment where business processes actually run. Development is a slimmer version with less disk, CPU, and RAM, isolated from production, and it's the first place you apply patches. Test covers QA, integration testing, user acceptance testing, and performance testing, ideally on the same hardware and software as production, and critically, it never writes to production. Sandbox provides read-only connections to production, gives users CRUD rights in their own separate space for proofs of concept and hypotheses, and likewise should never write back to production. An alternate production holds offline backups and provides failover and resiliency, identical to production. The exam point to remember: sandbox and test environments never write to production. Availability is the percentage of time a system or database can be used for productive work. For factors affected, and a handy mnemonic is MRRS. Manageability, the ability to create and maintain the environment. Recoverability, the ability to re-establish service after an interruption. Reliability, the ability to deliver service at specified levels for a stated period. And serviceability, the ability to identify, diagnose, and repair problems. On backups, a hot backup is taken while applications are running, with updates rolling forward or back on reload, while a cold backup is taken when the database is offline, which isn't viable if you need continuous availability. Best practice is to store backup files on a separate file system, back them up to a separate storage medium, and keep copies in a secure off-site facility. Remember MRRS for the availability factors. The work of this knowledge area splits into two activity groups. Managing database technology runs through understand, evaluate, and manage and monitor, and the evaluation step should start with a proof of concept. Managing the databases themselves covers understanding requirements, planning for business continuity, developing database instances, managing performance, managing test datasets, and managing data migration. The reference model for technology management is ITIL, the Information Technology Infrastructure Library, which was developed in the United Kingdom. And when selecting a DBMS, you weigh technical factors like architecture, scalability, and resiliency, but also non-technical ones, the organization's risk appetite, the supply of trained staff, the total cost of ownership, and the vendor's reputation and support. If asked for the technology management reference model, the answer is ITIL. Two more operational topics. Software configuration management has 4 procedures: configuration identification, where you identify, document, and baseline all the configuration attributes; configuration change control, the processes and approval stages for changing and rebaselining; configuration status accounting, recording and reporting on the baseline at any point in time; and configuration audits, which come in 2 types: physical, ensuring the system is installed per the detailed design documentation, and functional, ensuring the performance attributes are actually achieved. Data migration, meanwhile, follows the 5 phases on screen: design, extraction, remediation, load, and verification, and these are commonly repeated several times for moderate to high complexity migrations. Remember the migration sequence, DRLV, and the 2 audit types, physical and functional. When database performance degrades, the DMBOK lists common causes: memory allocation or contention, locking and blocking, which at its worst is deadlock, inaccurate database statistics, poorly coded SQL, inefficient complex table joins, insufficient indexing, competing application activity, overloaded servers, database volatility, and runaway queries, which you control with query governors. Of all these, the most common cause is poorly coded SQL. That's a likely exam point. On tools, you have data modeling tools, database monitoring tools that watch capacity and availability and alert the DBAs, database management tools for configuration and backup and cloning, and developer support tools that give a visual interface to the database. So, the single most common performance culprit is poorly coded SQL. A few techniques and governance points to close out the activities. The techniques: always test in lower environments first, starting at development and promoting upward. Follow physical naming standards, specifically ISO/IEC 11179 Part 5, the naming and identification principles, and place all changes and update scripts tested in non-production first. For governance, the metrics fall into 4 categories: storage, performance, operations, and service. And know the distinction between 2 evaluation concepts. A data audit evaluates a dataset against defined criteria to check compliance, while data validation evaluates stored data against established acceptance criteria to determine quality and usability. One more governance reality: track your software license agreements carefully, because being out of compliance carries serious financial and legal risk. Let's consolidate. ACID was coined by Herder and Reuter in 1983, with the concept established by Jim Gray. The CAP theorem is Brewer's, from 2000, pick 2 of 3. Base is basically available, soft state, eventual consistency. The technology management reference model is ITIL, developed in the UK. Schema on write is relational, schema on read is NoSQL. OLTP is row-oriented, OLAP is column-oriented. Blockchain is a federated, immutable database. Availability factors are MRRS. Data migration has 5 phases. There are 4 SCM procedures. The physical naming standard is ISO/IEC 11179 Part 5. And the governance metric categories are storage, performance, operations, and service. Review these until they're automatic. Let me point out the traps. First, the relational model is named for relational algebra, set theory, not for relations between tables. The exam plays on that misconception. Second, CAP does not let you have all three properties, you pick two, and choosing availability during a partition costs you consistency. Third, purging is permanent and unrecoverable, while archiving keeps data retrievable, don't confuse them. Fourth, RPO is your data loss tolerance and RTO is your restore time target, people reverse these constantly. And fifth, sandbox and test environments never write to production. One bonus, a blockchain is a federated database, not a standalone category. Know these and you'll dodge the chapter's favorite tricks. Let's wrap up. Data storage and operations designs, implements, and supports stored data. Its driver is business continuity, and its goals are availability, integrity, and performance. You've got the DBA types, production, application, procedural, development, and the NSA and the architectures, centralized, distributed, and federated, with blockchain as a federated example. ACID governs relational systems, Base governs NoSQL, and CAP says pick two. OLTP is row-oriented, OLAP is column-oriented, purging is permanent, RTO is restore time and RPO is data loss. Availability is MRRS, migration is DERLV, and the reference model is ITIL. That's Chapter 6. Let's test your knowledge with 5 questions on data storage and operations. Several of these turn on the precise meaning of an ACID, base, or CAP property, or on the RPO versus RTO distinction, so read carefully, decide on your answer, and then reveal the solution. Here we go. Question 1. A funds transfer must fully commit or fully roll back. Which ACID property? The answer is B, atomicity, the all-or-nothing, indivisible unit property. Consistency is about rules and integrity, durability about surviving failures, and isolation about concurrency. Question 2. Under CAP, when a partition occurs and the system stays available, what's sacrificed? The answer is D, consistency. Different nodes may temporarily return different values. You can't opt out of partition tolerance in a distributed system, and durability isn't even part of CAP. Question 3. How does base's soft state differ from ACID consistency? The answer is D, the system state may change over time even without new input, as data propagates across replicas. That's the essence of soft, in-flux state, the opposite of strong, immediate consistency. 2 more coming up on the next slide. Question 4. An SLA requires restoration within 4 hours and no more than 1 hour of lost transactions. Which metrics? The answer is D, RTO equals 4 hours, RPO equals 1 hour. RTO is the time to restore service, RPO is the tolerable data loss. Remember, the wrong options swap them or use unrelated metrics like MTTR and MTBF. Question 5. A 7-year retention policy that then requires secure deletion, how does it drive operations? The answer is B, it drives automated archiving jobs for aging records and purge jobs that permanently delete records past the 7-year limit, operationalizing compliance without manual effort. It doesn't mandate in-memory storage, indiscriminate annual purges, or the removal of backups. That completes Module 6. Next we move into Module 7, Data Security, another important and very practical chapter. I'll see you there. Slide 30.